So, welcome to Python on the Brain, a quick dive into NuPIC. This is a talk about cognitive computing, in case you hadn't figured that out from the brain part of this. I am Jeff Kramer. By day, I work at Hewlett-Packard on our Cloud Foundry and OpenStack integration, but by night, I like to play with cognitive computing stuff when I have time, which is not very often. So first a question, are there any cognitive computer neuroscientists in the room? Aside from you? You guys have to leave. I was at a Birds of a Feather session earlier this year at HP's Internal Technology Conference, and I was leading the brain one, and I am not a cognitive neuroscientist at all. And they tell you in the training session, you're probably going to be the least qualified person in the room. You can just assume that, but people won't speak up initially. So I started the talk and I was like, so what's everybody doing? And nobody wanted to say anything. So they were like, hey, why don't you tell us about cognitive computing? So I go off for like 15 minutes. And then it turns out that we had like two guys who were, the guys actually building HP's cognitive computing thing in the room. And I don't think I embarrass myself too much, but hopefully I won't hear either. You guys can just agree with everything I say, and that'll be good. So what are we talking about today? So we are talking about machines, computers that act more like us. And this has been the dream for a long time. We want machines that don't just respond to static rule sets, that have emergent behavior or seem to learn over time and act in somewhat slightly different ways than what we know and love. So back when we started out with AI, we thought if we just put enough rules into the system, the machine can logically step from thing to thing, and eventually we'll get emergent behavior. If there are enough rules in the system, it will know everything to think. We tried that approach for a while, and we thought it was going to be really easy. It turned out to not be so easy. And we have, expert systems. We kind of got, if you could build enough of a specific problem domain into a machine, maybe it can do that. But it can't do that for everything. So eventually, people decided, maybe what we need to do is we need to model how this works. Because we know that this works. So if we can figure out how this works, then if we can make a computer that kind of acts like that, then we'll have a computer that thinks. And if you look at projects like Europe's brain project, where they're actually trying to simulate the entire brain down to chemical level, that's like the far side of the simulation spectrum. Really hardcore, like it's not going to be fast, but we're going to figure out how the brain actually works. And on the other side, you have neural networks stacked in layers, and it's enough like the brain that it can sort of act like that. And most scientists seem to fall somewhere on that spectrum, either more on the simulation side or more on the abstraction side. So in this talk, I'm specifically talking about NuPIC. NuPIC is an open source project from a company called Numenta, which also used to be Grok Systems. Numenta was started by Jeff Hawkins, and that is Jeff Hawkins right there. You may know Jeff Hawkins because he co-founded Palm and Handspring. Before he developed graffiti and went on to do those things, he was actually really interested in the brain and how the brain worked. And he couldn't get into the MIT AI lab, so he went off and did Palm and Handspring. But after he was able to indulge his passion. So he wrote a book called On Intelligence, which I have a signed copy of here. And if you ask me a good question, it could be yours.
Do they have to be hard questions or easy questions?
They have to be relevant questions. How about that? And after he wrote On Intelligence, he founded Numenta, a company to build a system that actually puts the ideas in the book into practice. Numenta open sourced NuPIC at OSCON last year, which is where I found out about it. There's a video of that online if you want to watch it. It's pretty interesting. So what is it about the brain that helps it learn? How does all this stuff kind of tie together? So what we're talking about when we're talking about the brain, we're talking about the neocortex. The neocortex sort of holds what is you. It's the sum of your experiences. And it's about the size of a dinner napkin. It's about the thickness of like 7 business cards. And it is actually made up of 7 layers, not like the dip, but sort of kind of like the dip. And it has regions in it, and the regions talk to each other. But it's kind of general purpose computing. In rats, they've actually like disconnected, the auditory input and put it where the visual input goes and swap them the other ways, and the rats continue to be able to function. So it's not a specialized thing, it's kind of a general thing. And what it does is it constantly matches patterns and predicts what it will see next. And this is how you function as a human being, because the world is very complicated and things happen all the time, and if you tried to actually understand what was happening all the time, you would not be able to function. But your brain's constantly saying, okay, I'm standing here, the floor is not going to drop out from under me, and that prediction is generally constantly upheld. And when the prediction fails, there's a spike that goes down the system and says, hey, what I predicted to have happened didn't happen, so we need to pay attention right now. So pattern recognition and prediction is what the brain does a lot of the time. And if you do prediction, the opposite of that, you can get anomaly detection. So you can say, this was way out of bounds from what I predicted, or no, this is pretty much what I predicted. So when we try and model this into a computer, the way that it works when sensory data comes into your brain, so you have like your visual input, and you may be reading the word layers up there. Even though it's misspelled, you can recognize it. So the first level in your brain where your optic nerve comes in, it may say, oh, I see, a vertical line, a horizontal line. I see a little circle next to it, a curve. And it decides that that's what it sees, and it passes that information up to the next layer. Synapses fire, and the next set of neurons say, oh, okay, you saw some lines and some circles in this formation. And when you're just learning to read, it will say, oh, this is an L. And then the next thing after that is an A. But as we become more used to these things, we actually, as human beings, we pattern match entire words, which is why we can, understand words that are misspelled at a glance, even though they're misspelled. So you're sort of feeding up higher and higher in this stack of areas of the brain. But when you hear the word layers come in through your auditory system, you're matching, sound waves instead. But eventually it all connects, and the concept of layers and what layers are exists in one place in your brain, and you can get to it through your visual system or through your auditory system. And inside of each of those, it's made up of neurons and stuff. Columns of neurons, sort of in a sheet. The neurons are connected to each other via synapses. And they fire. And a specific pattern of neurons that are activated is how your brain does pattern matching. It says, oh, I've seen this before. And the synapses that are connected to a specific neuron, let's say there's a neuron that fires when you hear the word layers. And if you're from Texas or from the US, you will probably also have some neurons in your brain that connect to party dip. And those synapses, when you hear layers, the synapses will fire, and they will sort of warm up the connections to things that you have seen right after layers historically. So you've seen 7-layer party dip before. So there are synapses in your brain that connect those two things. So that when you hear party dip, that connection strengthens. So it learns over time, and those connections strengthen over time because you saw the patterns repeated. So that's how it works in your brain. So how do you implement that in software? And this is where we get to encoding problems and sparse distributed representations. So software doesn't, it doesn't have neurons, but it needs sort of that sheet of columns to exist where some of them firing can represent a thing. And sort of to oversimplify, neurons can either be in an on state or an off state, which maps to ones and zeros pretty well. So in the field of cognitive computing of systems like NuPIC, they deal with sparse distributed representations. And these are bitmap representations of them. And you can see the cat and the dog one, I hope. So it's just a big list of ones and zeros. Mostly zeros, a few ones, and it represents the idea of cat and dog. In this case, this comes out of a project called CEPT, which is now known as cortical.io, which is a API-based system where you can feed it words and it'll feed you back something like this. And you can see up here we have cat and dog, and you can see that these two things, although they're different bitmaps, they sort of overlap in some cases. And the job of the encoder is to make sure that things that are similar feel similar to the system. So if I sent spoon through and put up a picture of spoon, it would not have significant overlap with cat and dog. But because cat and dog are, semantically similar, they share concepts, they are similar in the encoding. And if I put up, collie, it would have a lot of overlap with dog, but less overlap with cat. So we have encoders. Encoders create sparse distributed representations of things, and then we have to learn that stuff over time. And once we feed all this stuff into the system, NuPIC specifically is what we call an online learning system. So you can feed it data. You don't tell it anything about the data to begin with. You just start feeding it stuff. And it can start making predictions about the future. And in the beginning, it's very bad at it. But over time, as you feed it more and more data, it starts to get better. This is from a demo called Hot Gym. They have a CSV data set of a bunch of power consumption from a gymnasium, I think maybe in Australia. And they feed it into an encoder with, here's our power consumption value and here's our timestamp. And they feed it in over time. And initially, the prediction trails. It basically says, oh, I think I'm going to see what I just saw next. But after about a week or so, it actually starts to lead the prediction. So they demoed this at OSCON. I think there's a video of that presentation. And you can download the source code. This is all open source now. And it also does anomaly detection. So you can say, what did you think you were going to get? Here's what we actually got. And it can score, hey, that's really out of bounds, or that's just a little out of bounds. These are anomalies for offshore wind turbines. So I'm not sure if this is like braking data or energy production data, but you can say, hey, things aren't operating how we think they should. And it's not based on a specific rule set. It's just sort of the gut feeling of the brain that you have created. So now I'm going to show a quick bit of code, and I'm going to try and do a demo, and hopefully it will work. I'll put that over here for video purposes. Can everybody see that? Okay. So at the top, we do some audio inputs. What this script does is it reads in microphone input from my machine and converts it into an integer decibel value. It takes that integer value, encodes it into a sparse distributed representation of a number, and then it feeds it into something called a temporal pooler. And the temporal pooler in NuPIC is how it learns over time and how it makes predictions. It's a system that remembers. And then we try and get it to guess what kind of audio level it's going to hear next. And the hope is that you can all be coordinated enough that we can all make a sound at the same time and actually have it predict that. So we import Pi audio, some math stuff to do our decibel calculations. We import the scalar encoder. There are also encoders for dates, different systems have encoders for images. Quality of encoders is really important. The job of the encoder is to group like things. So the way the scalar encoder works is you tell it, like, put numbers into buckets. So if you're going to give it numbers from 0 to 100, the numbers like 3, 4, and 5 are pretty similar in its consideration of things. So that's how the scalar encoder works. This W bit is actually how big those buckets should be, I think. So this is number of columns that you're going to output, your minimum value and your maximum value. And then we create a temporal pooler, and the number of columns, cells per column. There are a bunch of fiddly knobs in here that you can mess with. I messed with it for about half a day and couldn't get it to learn anything, and then realized that my activation threshold was too high for my bucket. There's a lot to learn here. Fortunately, there are some good resources. So then we're going to set up a Pi audio stream. I'm basically going to open the microphone on my machine, and then we're going to do a loop. And in our loop, we're going to grab some audio input. We are going to turn it into a decibel measurement. Then we're going to encode that into a sparse distributed representation. We're going to feed it into our temporal pooler and have it learn and compute inference output, so predict what's going to happen next. And then, assuming it predicted anything, we are going to try and figure out what it thought it was going to predict. And then we're going to print that out. The temporal pooler learns best if you can tell it this was one cycle. So if you were trying to have it learn data over a day, you would reset every night so it knew that, okay, that was one cycle. It learns faster that way. So we don't have cycles necessarily, but we're just going to reset it every 20 samples we feed it. Okay. So we're going to try some group participation here. I don't know how well this is going to work, but it's an experiment. Okay, so there we go. Okay, it's pretty loud in here. So I'm going to raise my arm. I'm going to count to 3. And when I count to 3 and I drop it, everybody's going to clap. Do we think we can do that? Sunday afternoon, you guys are motivated and peppy? Okay, good. Okay, so let's try it. 1, 2, 3. Just once. Just once. We need to get some spikes in here. Okay. Okay, so we have a bunch of bad data in our system right now, so I'm going to restart this thing, and everybody be quiet. Okay, so we got a prediction. This prediction here. I'm going to call this victory. You guys can download this code and try it at home. But it was like, hey, where's my next clap? So at least that's what I'm going to say that it predicted. Sorry, the line right under reset. So the predicted decibel rating was really high, and it did not get it. Okay, back to my presentation, which is here. Okay, so tiny glimpse of what NuPIC does and cognitive computing and how all this stuff works. If you are interested in more, there is a NuPIC email list that is pretty active. Matt Taylor is their community guy, evangelist. He's pretty accessible. They have hackathons twice a year, maybe more. Unfortunately, they are so far in the Bay Area. But there are some pretty cool videos from those where people have built like tic-tac-toe systems, or they taught like a quadcopter to fly with it, which is pretty neat. Jeff Hawkins talks a lot, so there are a lot of videos of him speaking. He is much better at explaining how all this stuff works than I am. The book is good. Ray Kurzweil also has a book called How to Create a Mind, which covers a bit more of the anatomy too, which is nice and accessible. There's cortical.io. They don't have Python libraries. They have Java bindings, but the API seems fairly simple, so you can get an API key, and I think it's free to use. A lot of the stuff has been tied up if you're looking for a search keyword in the DARPA Synapse program. The DARPA Synapse program was an effort to create a brain on a chip. If you've seen IBM's North Point processor that they announced a couple months ago, maybe, it's a bunch of tiny little compute units really close together on a processor with a little bit of memory. And it's designed to be able to run these things really well, really fast. Because we've reached the point where in software, we can't get it fast enough to do useful things like video image recognition. It's just not fast enough. This is something really cool that hit.
Is that what Jeff says too?
Yeah. So they were involved in that program. So 3 weeks ago, somebody sent an email to the NuPIC hackers list and was like, hey, I created this thing. It's like an IDE for developing NuPIC applications and visualizing what's actually going on inside the temporal pooler. And everybody was like, wow, that's pretty cool. I haven't downloaded it and played with it myself, but I believe it is all Python. The Python bindings for NuPIC are first level for them. They're sort of the recommended way to interact. It's C++ under the covers, but the libraries are really good. And that's it. The code is up on the GitHub repo along with these slides. I am Jeff K on Twitter. Questions? Yes? I don't rightly know. Thoughts?
What was the question?
Model of the neuron that they're using?
Well, this is sparse distributed coding, so there's not a single neuron. It's that encoder that you put.
Right.
It's actually creating a whole bunch of points out there, so it's like a CDMA for the brain. And so it's not a single neuron that's firing, it's a collection of them. And that pattern is orthogonal to all the other patterns in a CDMA-like way. So it's using sparse distributed coding, which is Pente-Canerva's work from the 80s. And Pente-Canerva was working with them. There's a book out there that Canerva put out.
Yes?
I think what it does is I think it tries to replicate what are probably equivalent cortical columns.
Right.
Cortical mini columns. And if you read the paper that I think you got those drawings from, at least there is a paper that he did that had the drawings that you had.
Yeah.
It actually pretty much describes the algorithm that they use.
Yeah, so they...
Not the exact detail, but it
Yeah.
describes it in pretty
So they have
detail.
they call it the CLA, the cortical learning algorithm, which is what they they wrote this white paper first, and it's available for download. In the last year, I think Jeff has had some different ideas about how he wants to do learning over time. I don't think they've gotten around to actually implementing those things, but the white paper is available. And yeah, I think these graphics are from that.
Different name for the temporal stuff too, right? Isn't it?
Yeah, the temporal puller is really, yeah, it's badly
The name
named.
for that label, I haven't heard it called cortical learning algorithm, or something else they have called it for a while.
Yeah.
Do you have any examples for text-based interface, like conversation?
Yeah, so in one of the hackathons, somebody tried to create like somebody's been working on like a predictive spell checker using it. Somebody tried to make like you feed in a giant library of text and then you give it one word and you try and have it like predict words after that. I don't think they got very far with it because every time when I run it, it gets to like a the, and it just gets into this loop of just the, because it's like the most common word. But yeah, there are some good hackathon examples, and they have a lot of videos they've been recording, and I think they start live streaming them recently too. So.
A historical note is that originally he didn't use sparse distributed coding, he was using Bayesian mathematics. And then he finally switched to sparse distributed coding. And some of his talks basically says, if you're not using sparse distributed coding, you're not using AI. You're not doing AI. So he's really come full circle around
Yeah, I mean,
using these techniques. So.
it's interesting. They seem to be very open to changing their ideas. You know, they really want to get it right. But people in this field have a lot of strong opinions.
We're over time.
Okay. Cool. So thank you, everybody. I have stickers if you would like a sticker. And would you want to?